I am Philip Filippo and I am Professor of Structural Engineering at UC Berkeley. I have the honor of welcoming today's guest, Professor Paolacci from the University of Rome. And since Rome has 3 universities, he comes from number 3. They are in no particular order, but there are 3 of them. Professor Paolacci actually is a student of the University of Rome La Sapienza, the first university, and he graduated there in 1992. He continued to do his PhD work with Professor Vincenzo Ciampi, and he's moved to the University of Rome Tre, as they call it, of 3, in 2001. Throughout his work, throughout his research, he has been working on earthquake-resistant analysis and design, and in particular, in the last few years, he has broadened the scope of the investigation to consider risk of petrochemical facilities, which is a much more interdisciplinary topic. And he will be reporting to us today about this and many other things. And we are delighted to have you here. Thank you for coming.
Thank you, Philip.
We look forward to it.
It is really a great pleasure to be here. Actually, after 16 years, because I've been here as a scholar. And I have had the pleasure to enjoy the Berkeley University, and now it is really a great pleasure to be here presenting some of the outcomes of a research of my research team concerning probabilistic risk assessment of petrochemical plants under seismic loading. This is as Philip told us, is a multidisciplinary matter in which you will see most of the parts are not concerning structural engineers, but rather industrial engineers. But we will see how they are related to each other. This is the goal of the presentation. And so this is the outline. Oh, one is missing. Yes. So I will show you some premises just to understand the problem, how or where we want to go, and what we want to propose to solve the problem, to calculate the risk of petrochemical plants. Then I will show you what is the strategy. What is the strategy to deal with the problem. Then some motivation for a new quantitative seismic risk analysis for industrial plants, in particular for process plants. And then we will speak about proposal of a new methodology for the seismic risk analysis of petrochemical plants. And then, given that we completed the research and we implemented this in a software, it will be a pleasure to show you how this software Priamos works. And then some conclusions I hope useful for you. Okay, this is the University Roma Tre. This is a young university, but it's very active. Okay, I'm in the Department of Engineering, and there is a special section of civil engineering, which we usually do experimental and numerical investigation of structures. This is our laboratory. This is a new building that's been constructed a few years ago, and these are some of the students of us. So we are, very active in several fields. This department has a very large interest, including structural engineering, but not only mechanical, information technology, and electronic engineering. So we are working together with a unique goal for the development of engineering matters. So these are the research topics concerning my research team. Just to be brief, you can see there is a broad range of interest. Performance-based design of steel concrete composite bridges. We just concluded a European project about this. There's some publication going to be published about this topic. Then assessment and reduction of seismic risk of reinforcing concrete buildings and bridges. Also, this is we are really interested in, and we made a lot of experimental tests on this topic, and also we published several papers on this. Then seismic risk of measure hazard industrial plants and applicability of seismic protection system, base isolation and energy dissipation. This is will be the topic of today, actually a part of this research. And then we also made some years of research about the seismic vulnerability of high voltage electric equipment. I saw that also in your laboratory. You have some stuff of this. We propose an innovative seismic protection system to reduce the response of this kind of structures. So, this is more or less a quick overview of what we are doing. What about process plants? Because this will be the main topic of today. So, as you should know, the importance of industrial facility of today, in particular refineries, is in a modern world societies is very high. In a world, as written there, that has continuous need of materials, of petrochemicals. Okay. The importance of petrochemical plants is clear. Okay, so of course, given that we are structural engineers, we are mainly interested in the main components of plants. We are speaking about of storage tanks, process equipment, pipelines, torsion flares, with each with the proper functionality. Okay. But they are connected each other, not in a structural sense, but in a functional sense. So this means that we need to understand how they work together, and in case of seismic action, how they interact together. So this is the main goal to dealing with risk in the seismic conditions. So this is as you know, probably, this is a typical layout of petrochemical refinery, in which most of the parts are occupied by tanks, storage tanks, in which most of the hazardous material is stored. So we are really particularly interested in this kind of structures, and we made a lot of effort in doing research about this, including fragility analysis of this kind of structures. So this is very interesting, and also some studies about seismic protection of them. But also we have process equipment and other parts of the plants, including office area in which there is the control room of the plant, and this is usually is a matter of civil engineers rather than process engineers, but we are interested also in this. But I have to say that in the remaining part of the presentation, we will focus on what happens when the seismic action will act to the storage tanks farms, in which in the past several problems happen. This is an overview of the several industrial accidents happened in the past. You can see here we have earthquakes that is only 8% with respect to the 56% for lighting, with respect to lighting. But the consequences related to the earthquakes could be larger than lighting or wind or flows. So given that during an earthquake we could have, or we will surely have, multiple simultaneous failure of industrial components interacting to each other, creating a so-called domino effects, in which so there are very good examples of this. Tupras refinery in 1999, in the Izmit earthquake, or the Tohoku earthquake in 2011 in Japan. So these are a good example in which important problems like this happen. This is the Tohoku earthquake, in which many petrochemical plants were affected by earthquakes with clear effects, leakage of hazardous materials, and sometimes problems like this in which there is a pollution, let's say, and fire sometimes, but sometimes great explosions like in the Chiba refinery, in which the structural problem, like this, is transformed in a huge problem due to the leakage of gas inside, and then creating the so-called vapor cloud explosion. There were the conditions to trigger the explosion and causing effects like this. Also in Europe, I mean, we are interested in this because this is a map of refineries around Europe, and this is the well-known seismic map. So most of them are placed in a highly seismic zone. So this means that the evaluation of the risk of these plants is a real problem. Is a real problem. So what about Europe? So we are in Europe, and there is a very clear mandatory action that we need to take according to this European Union law, in which there is a special directive in which we are obliged to take control of major accident hazards involving dangerous substances, and in particular according to natural causes, the so-called Notic Event, natural technological events caused by earthquakes. This is a clear written. So this means that we need to deal with the problem. How to do this? It's really interesting, but we have to see the several steps to do this. This has stimulated several research projects on this topic. This is, the list of the most important ones, okay, in which Roma Tre actually was slightly involved in INDUCE project. These other research project that's been developed by other research teams, but all teams focused on the risk assessment and reduction of industrial plants. So this means that this problem has a stimulated interest in Europe, and research teams placed in Europe. For example, given that the owners of the plants have been aware of the problem, so what they did to solve the problem without a clear strategy in evaluating the risk, they increased the important factor. That's it. So this is, for example, what happens in France, Germany, Italy, Norway, just to give an overview. So there is a very clear inconsistency in return period values. So if we want to be, let's say, risk-based, if we want to take a risk-based approach, this is not the correct way. So we need to understand how to evaluate return periods in the risk-based framework, and this is not the correct way. You can see the differences between what is imposed by Eurocode and what is actually we have in the several countries, given these rough idea to increase the important factor. So of course also in USA, as you know, there are some guidelines, especially from ASHE, guidelines for seismic evaluation design of petrochemical facilities. So we know very well, but they are mainly based on, let's say, qualitative approaches, and without providing, let's say, a clear framework in which we should move to evaluate the risk. Also in Europe, let's say, given that currently we are trying to modify Eurocodes, several people are discussing how to include these aspects in Eurocodes, but without converging toward a unique view of the story. So this picture comes from the nuclear power plants, in which instead the strategy is very clear. So we try to understand if it's possible to mutuate this strategy for process plants. And this is what we did. And we will see in what sense. So on the Roma Tre site, what we did to deal with the problem. So this is the, let's say, a strategy that we adopted to solve the problem, a three-step strategy. The first one is component level, in which we want to understand the seismic behavior of these components and how they can be related to, let's say, leakage and propagation of damage. The second step is the plant level, in which we want to understand how these elements, the components, are interacting with each other during a seismic action. And the third one, that is still under development, is a community level, in which we want to see if, under an hazardous conditions, or what happens at the community level, especially take into account the way to calculate resilience, resilience of plants. These are more or less the three-step strategy. So today we want to focus on this second step. We developed this Induced to Safety project, in which several teams worked on components and interaction between the components during the seismic action. Okay, for the component level, we developed some experimental numerical investigations. Actually, Roma Tre was not the leading, was Thessaly, University of Thessaly, that you that you know, that led the project, and it was really interesting because we evaluated, the response with simplified, refined models of storage tanks or pressure vessels and other important elements like elevated tanks, for example, in which there are several real examples of damage. This is in Smith. So all these stuff, including also analysis of piping system, that is also important. We analyze some important fittings, including elbow, T-joints, vaulted flange joints, to understand the important engineering demand parameters under seismic point of view, and limit states, because limit states are one of the most important aspects, because we need to identify the most important limit states and the related loss of containment that can cause consequences. This was the main. Okay, we did also, of course, numerical simulation to prove the goodness of the analysis. You can see some numerical models with refined conditions. You can see here some models developed in Abacus, in which we finally found a very good agreement between experimental test and numerical test, as you can see. So this means that we are ready to introduce these in an evaluation of the response of components of process plants. So to be quick, this is the second step, plant level. So these are the several partners that has been involved in the development of this topic. University of Trento was the leader with Professor Burzi, and University of Roma Tre was involved in the development of a seismic risk methodology. This is the. So what we did, this is in brief, and then we will go step by step in detail. So, so we were interested, of course, first of all, in the assessment of the actual risk of so-called potentially dangerous onshore petrochemical plants, because petrochemical plants are one of the most diffused plants in countries, and can be related to important consequences, like Smith earthquake, for example, but not only. And then we had the idea to see how to relate these assessment, let's say, with inside the scope of Eurocode. This is what was the first step of the plant level approach. Then, of course, after this first step, we try to develop a full probabilistic quantitative risk assessment methodology using a consequence-based approach, cascading effect, let's say. How to do this? We will see that many of the ingredients are related to process engineering, okay? Because we are in a process plant and we have to see when an accident happens how the propagation of damage will spread it in the plant, and we have to see how to quantify the physical effects to the surrounding elements given an accident, and this is will concern cascading effect. We will also, of course, because we are structural engineers and we were mainly interested also in the structural response of the structure, we evaluated with several experimental and numerical investigation fragility analysis of the elements. Here you can see one of the tests that we did. This is what we did in France, in Saclay, in CA, concerning the response of storage tanks and building fragility curves, making some comparison with numerical and experimental tests. And then the last, one of the last steps was the issuing of a quantitative risk assessment provision for seismic loss prevention of this special risk. That means petrochemical plants with beyond design basis conditions. Yeah. And of course, now we are in the stage in issuing enhanced design recommendations. We are not ready to provide. I'm not ready to provide this, but we will sure ready in the next months because we are completing the. So motivation for these new QSRA procedures. So given the framework that I showed you before. Of course, given that we recognize that performance-based seismic engineering is a well accepted procedure for civil structures, we are asking ourselves what can be, in what way performance-based seismic analysis can be applied to facilities, to process plants. The problem is that the definition of limit states, of performances. So the performances in process plants are not clear. So for structural engineer, why? Because usually in industrial plants, two recognized limit states are accepted, especially in nuclear power plants. Probably you know, operating basis earthquake and safe shutdown earthquake. So how to link these two words? If you, so we made some analysis and of literature, and we discovered that operating basis earthquake actually means serviceability limit states, and the safe shutdown earthquake means, let's say, ultimate limit states. So in this case, we should have the plant with any damage with in operating conditions. Okay, the safe shutdown earthquake condition instead is a plant with some damage, okay, but allowing a safe shutdown. This is more or less the meaning. So the question is how to calculate the probability of occurrence of an earthquake related to these limit states to fill the table for industrial plants. So let me explain the what are the main issues in the probabilistic risk calculation of petrochemical plant. So this is the situation of nuclear power plant, in which we have a very well established conditions in terms of accidents, and we have a very well established path to follow the damage. This is the fault 3, as probably you know, and this means that we have only accident conditions and consequences. So this is a very well established procedure that you can find literature, but in case of non-nuclear power plant, this approach has some problems, because we should have this is clearly this is clear. We should have some accidents in more than one components, with the development of damage propagation conditions in more than one remaining component. So we have let's say more chains of accidents and a dynamic development of path, of damage path. So this means that we don't know, like in this case, in advance, how this path will develop. So we have to develop dynamically. So we need, of course, a strategy to deal with this problem. Of course, in literature, so I reported some papers that tried in the past to apply or to modify the classical QRA. We will speak about in a moment about QRA, classical QRA, but so all these very good papers failed in include a systematic procedure to analyze these chains of accidents. And above all, they use loss of containment frequencies that are not related to seismic actions. So also the domino effect that triggered seismic event is a topic that has been developed and studied a lot in the literature, but usually this research has been developed under seismic action, but in presence of nuclear power plant. Very few contribution has been provided for process plant. So in the classical QRA method, the quantitative risk assessment method, we have a situation like nuclear power plant, in which we have, given that we have damage, we have the identification of a source stem, release of material, then a dispersion model in the loss of containment effects, then evaluation of consequences model, physical effect evaluation, then vulnerability models for the evaluation of effects on equipment and people, and then estimation of risk in terms of economic losses or fatality or whatever. Okay, this is a typical approach. The problem that is here is this approach is not able to take into account multiple chains of accident, like we showed before, like in this case, in which like in this case, in which you can see, given an earthquake, we have the blue circle that represents units damaged. That can lead to consequences, the blue arrows, according to which we should have some damage, subsequent damage at level 1, and so on. Okay, this is the so-called multiple accident chain. So how to deal with this situation? Okay, we should in some way be able to predict a series of random initial scenarios and to see what happens during the development of during the propagation of damage. Okay, this approach, a multiple level approach, seems to be good to solve the problem. So what we did is to use the classical QRA, in which we have loss of containment events, certain dispersion, exposure and damage risk calculation, and we completed the framework with seismic hazard analysis, seismic vulnerability analysis to evaluate loss of containment effects, and during the exposure and damage, we implemented domino effects to arrive in the risk calculation stage. Okay, this is more or less what we did. Just to explain, if this is a plant, units, 6 units, for example, what we can do. So, at level 0, in which we have earthquake, no accidental conditions, we could evaluate the elements damaged by the earthquakes. Okay, this is the hazard curve. We can evaluate the intensity measure given a certain scenario. We can evaluate the probability of damage given the fragility curves, and we can establish which elements are damaged and can cause consequences. After that, we should evaluate the consequences in terms of loss of containment based on, this is a new proposal, loss of containment damage state matrix. That means that we have some damage conditions, damage states, and some loss of containments, and based on which we can evaluate which couple DS lock we have, and based on which what consequence we have with respect to the remaining undamaged elements. Okay, this is physical effects. Physical effects. How to do this? Antonio, my colleague, knows better than me this game, in which we work with the source unit. Source unit is one of these, damaged by the earthquake. And then, given a certain event tree, that means that you have a loss of containment event, you can follow a path of this, and you can evaluate which physical effect has been caused or is likely to be caused. Then, based on some known expression in literature for the evaluation of the effects in terms of thermal radiation over pressure, we can use the so-called probit models, in which this is a sort of fragility curves, in which you enter with the intensity measure of the effect, like in the earthquakes, but in this case we have overpressure or thermal radiation. You enter and you calculate the probability of damage. So given that, you can evaluate the level of damage in the target unit and evaluate in turn the consequence, the physical consequence, based once again on the event trees. So this is more or less the idea, and this story, of course, can continue at the subsequent level, because you have a level 1 with the green one damaged by the physical effect now, and based on the same story of before of this, we can evaluate the final stage. Okay. Of course, all this game is written here in red is a dynamic condition, in which all these effects are dynamically evaluated step by step. Okay, it's not possible to evaluate in advance. We have to propose a method to follow these possible ensemble of paths. Okay, of course, the propagation stops when no further propagation effects will take place, or when no further damage elements will be present, of course, when everything is gone. Okay, there are many possibilities to follow these ensemble of paths, but one of the, for us, one of the best methods is Monte Carlo simulation, because with Monte Carlo simulation you can generate all these several steps, identifying, of course, the random variables that have to be generated, and follow all the possible paths. So you can generate as so the number of scenarios that you deem necessary to calculate finally the statistic. And then to evaluate the probability of occurrence of a certain given scenario or a certain ensemble of scenarios. So this is the idea. These are the steps, and then I will explain step by step what we proposed. Of course, the first step is the classification of the plant equipment and the identification of the relevant limit states. Okay, the most critical ones, of course, including failure modes triggered by earthquake exposure. Of course. Then the second step is the evaluation of seismic hazard using, for example, probabilistic seismic hazard assessment methodology that is let's say, seen in this context. And of course, we should select seismic input for the evaluation of fragility curves. Then derivation of fragility curves for all equipment, of course, all critical equipments, of course, what we recognize as critical. Then we start with the several steps that I mentioned before. We have to determine the initial damage scenario using Monte Carlo sampling. So basing of fragility curves, we can extract, let's say, the number of initial scenarios, elements that are damaged by earthquakes, and this is called the level 0. Then we determine the loss of containment events for each component that is damaged by earthquakes according to established limit states. Then we have estimate the physical effect of each seismically damaged unit. Also here we can use Monte Carlo simulation because this can be extracted causally. You can notice that these three steps are considered as input because this can be done once and for all. Okay, the other steps instead are part of the dynamic evaluation of the story. Then we have, of course, damage propagation, the one that I showed you before, the levels greater than 1 with the procedure that we showed you before using event trees, probit models, and so on. Also in this case we use Monte Carlo simulation sampling in order to extract possible paths in a domino effect fashion. And then finally risk estimation and ranking scenarios, of course. We can make ranking scenarios and evaluate the most risky conditions, and then maybe to focus on most critical conditions. Let's say this is an overview of the of what I've described before. This is a flowchart of the method in which you see we random generate the seismic initial damage scenarios and consequences like this. We generate damage using Monte Carlo simulation based on fragility functions. We evaluate the consequences. Also here we have a random generation of consequences. Then we evaluate the physical effects given the damage. I'm speaking about overpressure, thermal radiation. And then, of course, when all the elements are finished, of course, we go to the next level. Otherwise, we can make the loop of the entire group of elements at the level 0, and so on. This is the same procedure in the level I, let's say, in which instead of using fragility function, we use probit functions, in which the intensity measure here is not the seismic intensity measure, but rather the intensity of the physical effects. So quickly, about the identification of plant components, you can read this paper that we wrote in 2013, in which we recognize for each structural typology which are the critical elements and what type of seismic observed damage can be analyzed. Okay, you can recognize, and based on this you can evaluate based on the experimental and numerical outcomes, evaluate the limit states associated to these damage conditions. Okay, this is the input data. Then, of course, I don't have to explain you how to deal with probabilistic seismic hazard analysis. So, of course, we need hazard curve. We need the response spectra. Usually, we use a uniform hazard spectrum according to a certain range of return period to be consistent with. But of course, in literature there are several methodology to select to scale earthquakes to evaluate fragility curves. So, in this case, we use, for example, cloud analysis method to generate fragility curves. But of course, it's possible to to do what you want. So also, this is the input table. Then fragility curves. Okay, we developed models. For example, we work with storage tanks mainly, in which several simple models have been proposed in literature, and we modify these a little bit to be more consistent with the experimental test. These are a couple of examples in which we have, for example, elephant foot buckling, as you know, or the roof, the floating roof sloshing damage, for example. But we could have also sliding, uplifting, and whatever. So we are able to take into account all possible damages, and we will see consequences. We are speaking about of into damage. Okay, for the for the further steps, the one that are that want to take into account all the propagation damage scenarios. So we start with damage scenarios at level 0. We generate randomly the damage conditions. So we extract, a number between randomly between 0 and 1, generated by using a uniform probability function. We establish if we have or not had damage. This is condition for which we have damage. Then, of course, we need to relate damage, if we have damage, to the loss of containment. How to do this? This is a problem on which we are studying, and for now the idea is to propose this damage loss of containment matrix. What does it mean? That the damage state is a damage that as a structural engineering we know very well. We are speaking about elephant foot buckling, diamond shaped buckling, sliding, overturning, blah blah blah. What is unknown is the loss of containment effects. So for now, what we did is to take classical loss of containment events that you can find in literature. There are many publications about this, and you can follow a deterministic relationship between damage states and loss of containment. For example, if you have sliding, is logical to think about loss of containment generated by continuous release for a full bore of pipe because of detachment of the pipe. And given that you know the diameter of the pipe, you can, and based on, of course, the level of filling of the tank, of course, you can establish the quantity of material that is released and the consequences. If you have leakage of liquid, of gas, or whatever. Then for the estimation of the physical effects, as you see, as you saw before, we use event trees. The event trees is a tool in which you enter with release conditions, and following some paths that I don't have time to explain you in details, you can evaluate the physical consequences. Pool fire, vapor cloud explosion, or whatever. These are some examples of them. So based on one of these, you can evaluate the effects in the surrounding area, and you can evaluate, for example, here the level of pressure that you have, and if, based on probability model, you have damage or not here. Okay, so you can enter here. Based on, for example, overpressure, you can enter here. Using probability models, typically probability models are linearized functions rather than functions like fragilities. So, but you know, it's easy to move from probit models to fragility models. It's very easy. So, but typically in the process industry, the linearized function is used. I mean, it's a matter of understanding. Okay. Then, of course, given that we know how to evaluate the consequences, we can follow the logical sequence of domino effect, because given that at level 0 you have some elements damaged by the seismic action, you can evaluate the physical effects, and based on the effects that you can calculate based on probit models, you can see if you have damage in the subsequent level, and so on. And so on. So, as a last step, of course, given that you generated a certain number of scenarios, of course, you can deal with these, you know, the evaluation of the risk in terms of 3 possible outcomes: scenario, outcomes, or fragility, or total risk analysis. What I mean, or you generate a seismic scenario based on you know, given a magnitude or in the distance and the site condition, you can generate the value of intensity measure at the site obtained by disaggregation, and therefore the outcomes are conditioned to the occurrence of the selected earthquakes. This is a possibility. The second possibility is to increase the level of intensity measure to see how the risk is changing. Or otherwise, you can integrate over the entire set of seismic conditions the results to obtain the total risk of a plant. And we will see how to do this. This is easy because given that we are using Monte Carlo simulation, it's enough, I mean, to apply for a scenario, of course, the medium value of the outcomes, number of summation of the positive cases with respect to the total number. This can be done for scenarios or, for example, economic losses. We can evaluate the losses given a certain scenario, and you can make a summation over the entire set of scenarios given a certain PGA. Or we can also calculate the total probability, the risk, total risk evaluation, integrating over the entire set of earthquake conditions. In this case, we generated also the earthquakes condition using sampling, magnitude from Gutenberg law, the distance, and the seismic activity, assuming a uniform annual rate of occurrence. To be more efficient, of course, we use important sampling because the number of simulation could be really high. So this is oriented, our simulation in toward the result in which we are interested in. And this, of course, in this case, we use some weights to take into account this. Okay, about the convergence of the method, we use the classical convergence criterion for Monte Carlo simulations. Practically, we establish a certain confidence interval and the maximum distance between the mean and the results, and calculating the coefficient of variation. And based on this formula, this is a coefficient of variation, we can evaluate the number of simulation that we need to obtain a certain probability. So all this stuff, and I almost conclude, has been implemented in software, MATLAB-based software. And you can see there are several, all these steps that I showed you before are in this framework. Of course, scenario, fragility, risk analysis has been implemented. And we have the possibility to include, in this case, tanks, but this can be expanded, to the elements in which we are interested in. But in this case, we implemented a condition for tanks. You can introduce all the information you need location, geometry, stored material, and so on. Then, of course, you can introduce the vulnerability function of tanks, fragility functions. We have also the possibility to generate automatically fragility curves included in the software. In this case, it's enough to calculate apart the fragilities and to introduce them in this section. Then we introduce a plant information, including condition which damage propagation can happen. Then we have atmospheric information, of course, because also in this case we need information, and these also are randomly generated because they are part of the story. And then analysis information. We should select the type of analysis that we want to perform, scenario, fragility, or risk analysis, in order to evaluate finally the risk. So the program is able to show you the geometry of the plant, in this case a tank farm. So we selected a tank farm. Here you see the several tanks and the characteristics, geometric characteristics, diameter, liquid level, height, and so on. Materials, and the program is able to converge toward a certain initial scenarios and domino levels. You can see the program is able to provide the seismic damage scenarios at level 0, in which you can find 0 damaged earth tanks, or in the second level, at the second position, 2 damaged earth tanks with this probability, 1.1, 10 minus 3, or the third, only tanks 9 with this probability, and so on. And each row is connected with other possible subsequent scenarios at first place, second, 3, 4. And you can see also in this case the probability of occurrence of the scenarios, and so on. Also, the single row could induce possible domino effect at the level 2. In this case, is indicated here, and this is the outcome of the software, in which you can see the red one that are the tanks damaged at the level 0, seismically damaged, and the orange one and the yellow one are damaged due to the propagation effects at the level 1, at the level 0. So, of course, the program provide for the single scenario like this the probability of occurrence. And so you can make a ranking in which you can decide if these, together with the owner, of course, you can decide if this condition is acceptable or not. In this case, of course, not, because we have the entire tank farm destroyed. And of course, it's possible also to calculate the frequency of the lost volume in the tanks. And you can decide if, and also relating these to the several domino levels. You can see here the expected loss of the content in 1 year, corresponding to the domino level 0, 1, 2, and you can decide if this is acceptable or not. Okay, so this is more or less the framework in which we are moved. So now we can draw some conclusions. Okay, so of course we established that the need to quantify the seismic risk of process plant has been clearly recognized. So of course, a specific action has been identified in order to integrate existing European codes on seismic risk of process plants to these aspects. Then, given that we have clear regulations that impose to quantify NATEC risk for process plant in general. This has stimulated our research, in which we identified the refinery as one of the most important typology on which we worked on. So we proposed a new procedure for quantitative risk analysis, take into account this is important, the domino effect within a process plant struck by an earthquake as a sequence of propagation steps, working with multiple level approach. Okay, for each propagation level we are able to identify the so-called level 0, the first level of damage, and the subsequent level effects, domino effects, in terms of releases, material releases, and physical effects to the surrounding elements. So, with respect to other methods that exist in the literature, I would like to stress these important aspects. So, this is an automatic generation or random initial scenarios based on probability of occurrence. And based on fragility curves that we know very well as structural engineers. So this is the link in which I think we were successful in proposing this fragility-based approach. So we also propose a direct association of damage states with the loss of containment with this damage states loss matrix. This is the first time that has been proposed. We are working on the definition of this relationship in the probabilistic sense. Now we assumed the relationship as deterministic, but of course this is not, and we are working on this. We have finally the possibility to adapt the risk output to the needs. If we need to know the probability of having a certain scenario, it's possible to evaluate it according to the procedure, or we can evaluate the economic losses, or also this is has not been shown, but it's also possible to evaluate number of injuries according as well to some probit models. And finally, the method can be implemented in any computer and programming environment. We use MATLAB, but I mean it's possible to extend these to other possible program languages and environments. And this software that now we are developing will be available, we hope, in some months in order to test it and to make a comparison with the alternative methodology. Finally, what I want to stress, this is very important, that the software that we proposed is certainly useful to evaluate the probability of occurrence of specific propagation effect as a domino effect. But we have also the possibility to adapt these to any other kind of NATEC events, not only earthquakes, because you can implement here also damage condition to the flooding or to the wind storms or whatever. So this is a very flexible framework in which we can move. And finally, last slide. Of course, we are interested in use this framework to evaluate what happens at the community level. So, given that we have a possibility to evaluate the risk of the entire plant, starting from this point, we want to know how these can affect the surrounding community. No? And this is a matter in which we are working currently with this good number of partners in Europe. And this is very interesting project because this is a Marie Curie project in which we have at now 14 PhD students working on this topic and developing subject like this, especially resilience, but not only resilience, also refining the procedure that I showed you before. Of course, all of this has been possible thanks to the presence of my colleague Antonio Caputo, that is expert on this. So I've spoken about things that Antonio knows very well, so thanks Antonio. And this just to say that the multidisciplinary character of this research has been the key, let's say, of the success. As a structural engineering, probably I would not be able to develop a framework like this. So we are rather happy, and we want to see what happened in the future, and making also collaboration with other institutes, university, maybe with Berkeley, who knows. So thank you for your attention, and so I would like to thank all the partners that have worked on this topic, including University of Trento and also SEA, and also some process plant owners, Engineering Fishbach, University of Thessaly, University of Liverpool, and Aachen University. That's been very exciting collaboration. Okay, so thank you very much for your attention.